All right, if you're on Zoom, please type something into the chat to let me know that you are here. The rule sheet is already circulating around for everybody who is physically present. So as Nathan pointed out a moment ago, we will be beginning our discussion of Cascode circuits today. Before we do that, I'm going to very briefly review some stuff. Let's see, remove this. With regards to BJT and Mosfet current sources and diode connected circuits. So as a review for our BJTs, make sure that's just everybody saying they're here. Yep, great. Since it's been a hot minute since we've looked at a BJT circuit, we implement a current source, specifically an NPN current source, by applying a fixed bias voltage to the base terminal of our NPN transistor and grounding our emitter terminal. For a PMOS, or excuse me, PNP current source, we have our emitter at VDD, our base terminal at a fixed voltage VB, and we open circuit our collector terminal. There's where we can take our output resistance, and our small signal model tells us that the output resistance seen looking into the output terminal of a current source should be what? Anybody remember? Our early voltage resistance there. Looking in through here. No. Give me just a second. I need to save this. Close this and reopen it so I don't get that silly error over and over again. So again, what should my output resistance be? Nobody recalls. That's exactly right. It is that simple. Our output resistance should just be R naught, which is the early voltage resistance that we see when we have effectively the base width modulation. Now, let's say instead of having a current source connection, we have a diode connected BJT. So for our diode connected, the collector and the base are at the same potential. Our emitter is at ground. We'll observe the same basic thing for our PMOS. Our emitter is at VDD. Tie these guys together. Look in. And from our small signal model, we have our base GM V pi R naught. Sorry, got ahead of myself. Wanted to write R pi there. Because it's diode connected, our base and our collector are tied together. Our emitter down here is grounded. We're looking in. Thoughts on what we see? So R pi in parallel with R naught. All right, that's most of it. So it'll be a 1 over GM as well, right? If we applied a voltage source here and measured the current flowing in, the current would split off through this resistor R naught, it would split off through this resistor R pi. And because V pi is the exact same thing as the test voltage, the ratio of the current that flows through this branch is just 1 over GM. Or the ratio between the voltage drop and the current flowing through that branch is 1 over GM. And so we have R pi in parallel with R naught in parallel with 1 over GM. All right, now let's take a moment to look at some MOSFETs real quick, and then we can dive right into the new stuff. So MOSFET current sources. We apply a fixed gate voltage, specifically for an NMOS. We tie the source to ground, leave the drain open. This is where we measure our output resistance. For PMOS, again, we apply a fixed gate voltage, VG. Here we have VDD, which is what our source is tied to. Our drain is open, and we measure our output resistance from here. Small signal model, we have this guy, GM VGS, in parallel with R naught. Here's where we're looking in. Here is our source, gate, drain. So what do we see? Just R naught, absolutely right. And lastly, for diode connected, again, well, I guess it's not again technically, but for diode connected MOSFETs, we should observe that our drain and our gate are tied to the same potential. So here's drain, gate, source. Source, gate, drain, looking in through here. And in both cases, PMOS and NMOS, we have something that looks like this. Oops. In through here. Here's, good God, what just happened? Drain, gate, and I don't know why I wrote E there because this isn't a BJT source. There we go. So what do we see? R naught in parallel with 1 over GM. Absolutely correct, because we know the voltage drop across our current source is VGS, so the ratio of the voltage divided by the current is simply 1 over GM. So our dependent source looks like a resistance, small signal style. All right, so now that all of that is out of the way, let's talk about the Cascode Bjt stage. And our first thing that we're going to talk about is the degenerated current source. So let's consider these two circuits. One will be for an NPN BJT, the other one will be for a PNP BJT. They're going to have identical small signal models. So unlike the book, I'm not going to waste time having an entirely separate section to talk about PNP. So we have a current source. I'm going to call both of these guys transistors Q1. One is PNP, one is NPN. The left one is NPN, the right one is PNP. What is the purpose of that emitter degeneration resistor? Anybody remember? Okay. Nobody remembers it. All right. Well, in our 4-resistor bias circuit, the purpose of the emitter degeneration resistor was to stabilize the operating point, to make it depend less on temperature and process variations. For a current source in particular, what it does is it boosts the output resistance of the circuit, or the output impedance of the circuit. The reason why we're looking at current sources in particular right now, as opposed to amplifiers like we have been doing, is because at this point, we're trying to focus in on what this degeneration does without worrying where our input signal or anything like that comes in from. And it's actually going to tie into when we start looking at cascoded amplifiers. So we should observe that for these BJT circuits, our output impedance is given by 1 plus GM RE in parallel with R pi multiplied by R naught plus RE in parallel with R pi. And this can be rewritten as 1 plus GM R naught multiplied by RE in parallel with R pi plus R naught. Two identical relationships. We're going to work an example in a moment, but we should pretty easily be able to see that this is going to be larger than R naught right off the gate, right? We're going to have 1 plus some number, which means our output impedance is being scaled, and then to that, we're adding another resistance of RE in parallel with R pi. So we're definitely seeing some number larger than our original value of R naught. So for the sake of argument, let's do a quick calculation. Let's say that we have a BJT current source. And we are given IC, our collector current is equal to 1 milliamp. We have a beta of 100, and we have an early voltage of 5 volts. We want to know what the output impedance is for this, and then also what it is if we degenerate it with a 100 ohm resistor, right? So without degeneration, we have R out is equal to R naught is equal to VA divided by IC, which we can see from our values very easily is going to be 5 kilo ohms, right? So we have a particular output resistance. With degeneration, where GM is equal to IC over VT and R pi is equal to beta VT over IC, our output resistance, R out, becomes 1 plus IC over VT times VA over IC multiplied by RE beta VT over IC divided by RE plus beta VT over IC plus VA over IC. And if we substitute in our numbers, we get 23.615 kilo ohms, right? So placing this 100 ohm resistor between our emitter and ground increased our output resistance by 372.3%. So that's a pretty significant boost in output impedance. There is, however, a trade-off, right? So if we are going to use an amplifier per se, so we allowed V in to have some sinusoidal value or whatever, we know that we need a specific collector emitter voltage in order to keep that guy operating within the forward active region, right? If we allow VCE to get below VBE, we're entering into soft saturation, and our output and our input aren't gonna, our output isn't gonna follow our input exactly. We're gonna see some distortion. Well, that emitter resistor is also carrying that current IC, or actually it's carrying 1 plus 1 over beta times IC, right? And so we are going to experience a voltage drop over that emitter resistance, which is going to limit the output swing of our amplifier, right? The maximum value that our amplifier could possibly output is VCC plus. The minimum value would be 0, but we're shifting everything up by the voltage drop over our emitter resistance. So degeneration does a great job, resistor degeneration does a great job of boosting the output impedance, but we also have to take into account that headspace or headroom trade-off. So in order to get around this, we can degenerate our current source with a transistor, right? So let's consider this guy. C1 and E1. So here's our basic current source, but instead of putting a resistor between the emitter and ground, we are going to put another NPN transistor. This is Q2. So we connect the collector of transistor 2 to the emitter of transistor 1, ground the emitter of transistor 2 like so, and now we measure our output impedance. The simplest way to look at this, or at least in my opinion, is like so. If I can draw to save my life today. So here's Q1, VB1. So effectively, we are just degenerating our transistor Q1 with the pretty high impedance of another current source, right? So the impedance of our current source is simply going to be R02. And the result of this, oops, went too far, is that we get 1 plus GM1 times R02 in parallel with R pi 1 multiplied by R01 plus R02 in parallel with R pi 1, which looks like GM1, R01, R02 in parallel with R pi 1 when GM1, R02 in parallel with R pi 1 is much greater than 1. Okay, so all I've done from our original equation is replace RE with R02. It's the exact same equation that I had earlier, and then we made a little simplification. I'm going to write down what a Cascode PNP current source looks like as well, just for the sake of argument. Then we'll talk about some stuff. One, take that back. Q2, Q1, emitter, base, collector, emitter, base, collector. All right. So, give you guys a moment to write things down here. This process of degenerating with a transistor is called cascoding, okay? That name comes from old vacuum tube terminology, where it literally means something like cascoding a triode, blah, 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 something with a pentode. None of that makes a damn bit of sense to any of us because this isn't pre-World War II. And we get to use semiconductor-based devices. So it's cascoding is what it's called. we would say that transistor Q1 in each case is our cascode transistor, and transistor Q2 in each case is our degeneration transistor, if we're trying to keep up with our terminology here, okay? So it stands to reason that looking at our equation here, again, all I've done is replace RE with R02, but we've seen that the early effect resistance is typically a lot larger than what we would see with than putting a discrete resistor there, right? So if we had the exact same beta as before, with the exact same IC flowing through it, we should expect R02 in this case to be 5,000 as well, which is going to boost our output resistance significantly. The primary benefit of this is that our headroom requirement is a lot lessened. And what I mean by that is, as long as transistor VB1, or excuse me, transistor Q1 is deep within the forward active region, we can actually allow transistor Q2 to slip into soft saturation because it's being fed a fixed amount of current. So that voltage VCE2 can actually be pretty small, and this thing will still operate exactly how it's supposed to. So we can allow one of those transistors to slip into soft saturation, which gives us more voltage headroom at our output. So just as a quick example, is there enough room down here? No, okay. Let's calculate the output resistance of the cascoded BJT. VB1, VB2, Q1, this is Q2. Let's say that IC1 is identical to IC2, is 1 milliamp. Beta 1 is equal to beta 2 is equal to 100. And our early voltage VA1 is equal to VA2 is equal to 5 volts. So effectively, we're cascoding this guy with a completely identical NPN transistor. Our output resistance would be IC over VT, that's GM, times VA over IC, that is R01, multiplied by VA over IC, that's R02, multiplied by beta VT over IC, which is R pi, and then we're going to have VA over IC plus beta VT over IC. And we get a value of 328.9 kiloohms. So we have an increase of 1,293% in output resistance as compared to our resistor degeneration scheme. And we have an increase of 6,479% as compared to no degeneration whatsoever. So we can really, really boost the output resistance of our configuration here by using a cascoded scheme. Now, here's a question for you guys. Is there a limit to what resistance can reach? So for example, if we tried to cascode with an ideal current source as opposed to a NPN transistor current source, what would R02 be? We had an ideal current source. What's the output, or what's the impedance of an ideal current source? Anybody recall that from circuits 1? Infinitely large, okay? So what happens if we replace R02 with infinity? So R02 in parallel with R pi 1 just becomes R pi 1. So we'll have 1 plus GM R pi 1, R01 plus R pi 1, which means effectively as R02 approaches infinity, R out approaches GM1, R pi 1, R naught 1, which is approximately equal to beta times R naught 1. So we have a maximum possible output impedance when we have a cascoded BJT current source, okay? This is caused by the finite input impedance of the BJT. And so let me explain what I mean by that. So if we have our circuit, where we degenerate this guy with an ideal current source, our small signal model representation of this guy is going to look something like this. We're measuring R out by looking into the collector terminal. Right? Because we have an open circuit here, if we applied our test voltage source, our test current is required to flow through that input impedance. So that is the limiting factor here. The presence of a non-infinite input impedance is what puts a finite value on our output impedance. So it's an interesting relationship there. So we could look at this guy and see that its output impedance is GM1, R01, R pi 1 plus R01 plus R pi 1, which is again approximately beta times R01. So we're making an assumption here that that multiplicative term is larger than those individual guys, which should practically always be the case. All right. Okay. So what effect does the early voltage have on our output impedance? Okay, so all of these circuits that we've been dealing with have some finite early voltage. We've been dealing with an early voltage of 5 volts. Let's see what happens if we increase the early voltage to 50 volts, okay? So first, let's say, how does the R out that we have right now compare to the maximum value? And then repeat the exact same thing for VA is equal to 50 volts. So we scaled up our early voltage by a factor of 10. So we have a better process to produce these guys, right? So we know that for VA is equal to 5 volts, our out was equal to 328.9 kilo ohms. R out max is going to be beta VA over IC. So that's 100 times 5 kilo ohms is 500 kilo ohms. And so for an early voltage of 5 volts, we see that our output impedance is roughly 2/3 of its theoretical maximum. So pretty good. For VA is equal to 50 volts, R out comes out to be 4.753 mega ohms. So we have a real big boost in output impedance. And R out max comes out to be 5 mega ohms. So having a larger early voltage caused it to go from roughly 67% up to 95%, right? So the bigger early voltage transistors we can pick for our circuits gives us the most boost to our output resistance. All right. So let's see, let's move on to page 4. All right. An alternative way to view a cascode stage is by treating Q1 as the transistor which establishes the operating point, or excuse me, treating Q2. So what I am suggesting is, and I don't particularly like this interpretation, I prefer the degeneration interpretation. But if we have a current source that has an output impedance R02, we can think of our cascode stage as simply stacking another high impedance stage on top of it, or loading it with an additional high impedance stage, right? So if this voltage is the one that sets the current level, then this guy on top, its whole job is to boost the output impedance. GM1, R01, R02 in parallel with R pi 1. Just an alternative way of thinking about it. For the current source like this, to me, looking at it as a current source being degenerated by another current source makes more sense than this guy. But when we start looking at cascoded amplifiers, this type of interpretation is actually rather useful. So for instance, this is a quick aside here. What if I had a circuit like this? V out, and we're going to put a reference current up top here. And we won't worry about where that reference current comes from for right now. Everything below V out here looks pretty darn similar to what we've been dealing with, right? So we could think of it as Q1 being cascoded by something and do a whole bunch of work. But in my opinion, an easier way to quantify what's going on here is to think of this as a cascaded or two-stage amplifier, where on the bottom, we have a common emitter amplifier, and stacked on top of that is a common base amplifier, and you just multiply the two gains together, and you know what the output, the input-output relationship is, just like we did way back in circuits 2. Our textbook goes through 7 or 8 pages of doing it an entirely different way, based on the cascoded view from an amplifier perspective that I find to be difficult. I'm going to teach it to you on Wednesday, but to me, splitting it up into stages and figuring out what's going on is probably the easier route. Okay, so let's move along to a similar but different topic. What if I had the following circuit? Or similarly, I had this guy. Let's see, Q1, Q2, Q1, 2, VB1. So in all the previous examples, my cascoding was carried out by connecting an NPN transistor to an NPN transistor or a BJT transistor to a BJT transistor. But now I have effectively a complementary circuit that contains both an NPN transistor and a BJT transistor. Is this an effective method of cascoding or boosting the output impedance? Anybody have any thoughts? Pardon?
I would think still yes. You still want like
Okay, so let me draw the output resistance here thing because I'm missing it. So if we drew the small signal model for these guys, how is the degeneration transistor connected? So small signal model, well, let me label my terminals here, and this might help, all right? So obviously over here, I have the base 1, base 2, here I have base 2, base 1, collector 1, emitter 1, emitter 2, collector 2, collector 2, emitter 2, emitter 1, collector 1, okay? So small signal model, my collector of transistor Q2 and my base of transistor Q2 are at the same potential. Exact same thing for here. Collector of Q2 will be at ground because we're looking at a small signal model, so this voltage source VDD is turned off. Our base will also be connected to ground. So C2 and B2 in both cases are at the same potential. So these no longer look like current sources. They look like diode connected transistors. And a diode connected transistor has a significantly smaller output resistance because it is 3 quantities in parallel with each other, right? So these would fundamentally look like this. Where here we have 1 over GM2 in parallel with R02 in parallel with R pi 2 over here. Again, we have 1 over GM2 in parallel with R02 in parallel with R pi 2. Here's VDD. Here's R out. I don't believe that this is in the textbook, but it is an interesting thing because it's, as a student who might not be 100% sure of what's going on, this is a mistake somebody could easily make of, oh, well, let's just throw a PMOS in there and see what the hell happens, right? So if we throw this resistance as replacing RE into our original equation, what we get is R out is, this is going to get big and ugly, 1 plus GM1 multiplied by 1 over GM2 times, or excuse me, in parallel with R02, in parallel with R pi 2, in parallel with R pi 1, multiplied by R01, plus 1 over GM2, in parallel with R02, in parallel with R pi 2, in parallel with R pi 1. So let's calculate how this style of degeneration boosts our output impedance, where we consider this circuit U2, where IC1 is equal to IC2 is equal to 1 milliamp. Beta 1 is equal to beta 2 is equal to 100. And our early voltages VA1 is equal to VA2 is equal to 5 volts. We find that our output resistance, if we plug in all of our numbers, comes out to be 9.902 kiloohms, or approximately twice R01. So this actually does a worse job of boosting our output impedance than a simple resistor does. So it is obviously then to be avoided. So when you're going to cascode anything, when we're going to be doing a whole heck of a lot of it, you always want to make sure that you're cascoding with a same technology transistor, right? So if you use an NPN, you degenerate it with an NPN. If you use a PNP, you degenerate it with a PNP. If you use an N MOSFET, you degenerate it with a N MOSFET, etc. There is a technique called folded cascode, which is beyond the scope of this course. We go over it in 438 for those of you who haven't had enough of this by the end of this quarter and want to do more of it in the spring, where you effectively fold at the cascode node with an opposite technology transistor, but it's configured in such a way to where it doesn't jack things up like this. It's hard to describe without getting into great detail about it. So there is a use for connecting an NPN to a PNP, etc. But this configuration isn't how to do it correctly. Folded cascode structures are used when you have very, very low supply voltages because they take up extremely small amounts of headroom, but they don't give you nearly the gain that you would see from this configuration. All right, so that is the Cascoded BJT stage. Anybody got any questions or anything before we move along to Mosfets? All right, so very, very high level summary. We're doing this, we're degenerating our current sources to boost their output impedance. We have seen that degenerating with a transistor or cascoding boosts it to a larger value with a smaller consumed headroom. So generally speaking, it's all positives, all right? If we cascode with the opposite type of transistor, it screws everything up, so don't do it. All right, so our last topic for the day, this one's going to be relatively short, is the Cascoded Mosfet stage. And we will again start with degenerated current sources. So we might have an NMOS current source degenerated by some source resistance RS, where I'm holding my gate voltage to be a constant value. My drain is open circuited. My source is doing whatever it needs to be. Here's my output resistance. Or similarly, for a PMOS, I have my source degeneration resistor between VDD and the source. My drain is still open circuited. And I have a fixed voltage applied at my gate M1 and also M1. So based on our prior analysis, we know that the output resistance of such a current source should come out to be 1 plus GM times RS multiplied by R naught plus RS, and we can also express this as 1 plus GM R naught times RS plus R naught, like so. The problem with degenerating with a resistor is the exact same as we saw with BJTs. We are getting a boost in the output impedance, fairly obvious from the math, but we are also losing headroom because we know that that degeneration resistor RS has to be carrying a current equal to the drain current. And so we are having a voltage drop occur over that transistor RS, which is effectively raising the level of our gate source voltage to be operating in saturation, which is then confining the amount of voltage that we can see at the output with respect to our power supply voltage, VDD. So we still have that headroom limitation that is occurring. We can negate some of that trade-off by, again, cascoding or degenerating with a transistor. So that would look like this, where we have our NMOS transistor being degenerated by another NMOS transistor. This is M1, so that's our Cascode transistor. This is M2, so that's our degeneration transistor. Here's our output. And this guy looks like this. And I'll draw the PMOSs as well while I'm at it. In turn, looks like this guy. And just by replacing RS with R02, we find that our output resistance, R out, looks like R01 plus R02 plus GM R01 R02, which is approximately GM1 R01 R02 when GM1 R01 R02 is greater than R01 and R02. And as we'll see in a moment in a numerical example, that is pretty much always going to be the case. Yes, ma'am. This is R02. Yes. Always being degenerated by R02. So we're just looking at the degeneration transistor as the output impedance of a current source. And the degeneration transistor I've labeled as transistor 2 in everything that I've drawn today. All right, at least I meant to. Let me put it there in case I made some sort of dumb mistake. So, got a numerical example for us to look at in a moment, but one thing that we can look at pretty easily here, is there an upper bound on the output impedance of a cascoded Mosfet stage? No. The larger we can make R02, this guy's just going to keep going up and up and up. And the reason why that happens is the exact opposite of the reason why the BJT stage was restricted. We have an infinite input impedance at very low frequencies, which means our gain can go up and up and up. For the BJT, we are limited by having a finite input impedance of R pi. That's what keeps it clamped down to, you know, a couple of hundred kiloohms to mega ohms or whatever, depending on what our early voltage is. This guy, sky's the limit. Just like in BJTs, we can treat transistor 2 as the one that is establishing our operating point, and then we're simply loading it with another high impedance transistor, which is causing our output gain to boost. Again, it's the exact same concept as before, no big deal. So let's wrap things up. We've got 15 minutes left. I feel like this will take maybe 5 to 10 at most, with a final example problem. Let's say that we have an NMOS current source. Transistor M1. And we have it biased in such a way that we have a drain current of 200 microamps. We have a mu NCox of 100 microamps per volt squared, an aspect ratio of 10/2, and a channel length modulation coefficient of 0.1 per volts. I want to know what our out is without degeneration. With a source to generation resistance of 2 kilo ohms. We can get away with a 2 kilo ohm resistor in this case because our drain current is so small that it's only going to be about 400 millivolts of headroom being lost. And finally, cascoding with an identical transistor. All right. So without degeneration, we know that our output resistance is R naught, which is 1 over lambda ID, simply 50 kilo ohms. So pretty large output resistance already. With a degeneration resistance of 2 kilo ohms, we're going to need to know our transconductance. So that is root 2 mu n Cox W over L times ID gives us 447.214 millisiemens. Our out is 1 plus GM R naught 1 RS plus R naught 1. Plugging in my values, I get 96.721 kilo ohms. So a 2 kilo ohm resistor is enough to effectively double the output impedance. So we actually see that degenerating with a resistor for a Mosfet scheme doesn't do as good of a job as a BJT, even when they're consuming roughly the same amount of headroom. We don't get the same boost. With our cascode, and recognizing that R naught 1 is going to be the exact same thing as R naught 2, we get R out approximately GM1 times R naught 1 times R naught 2 to be 1.118 mega ohms. So that's a hell of a boost, right? We do have a constraint in as much as our second transistor needs to be operating in the saturation region for this to occur. We can't get by with soft saturation and crap like that with a Mosfet. It's either saturated or it isn't. So this is cascoded Mosfets. One other question, I don't have any notes on this real quick, but I just thought about it. VG1 and VG2 here, or VB1 and VB2 for BJTs. Are they the same voltage or are they different voltages? They have to be different, right? Because in order for these guys to be operating in saturation or alternatively the forward active region, that's all based on the VGS for that particular transistor. So if we tie VG1 and VG2 together, the source for this transistor M2 is down here, but the source for transistor M1 is up here. It would force this guy into cutoff, so it wouldn't work correctly. So these are actually two different voltages. And typically speaking, like this guy is VGS plus 1 overdrive voltage, meaning we're biased it just far enough into the saturation region to where it can amplify our signal. And then this guy right here is that same VGS plus 2 overdrive voltages, which pushes it up enough to be operating in saturation. So that's just some qualitative analysis type stuff that we wind up doing a whole heck of a lot of in 438 because doing all this hard math is boring and I don't like it. So anyway, just wanted to point that out as another place where students could easily observe, oh, they must be the same thing. They can't be, or one of the transistors turns off. You have to be able to accommodate that. Scroll down. Too far, obviously. All right. So getting out 5 minutes early. On Wednesday, we're going to talk about cascoded amplifiers. I'm not sure how long that will take because the book I don't think does a super great job of it, so I might elaborate on it a bit more. Or we may wrap that up a little bit early and get into current mirrors, which is a very, very important topic. Current mirror is like a fundamental building block of most good amplifiers. All right, see you guys Wednesday.